time we started section 4.3 and we were talking about greatest common divisors and least common multiples. We didn't get to least common multiples, we were still working on divisors, okay? So greatest common divisors is the largest divisor, the largest value that will divide two or more numbers. And we encountered a few different ways of doing that last time. The last one that we left off on was one of my sort of newfound favorites. Once your book shows how to do this particular one, I know some of you like it too, where you were looking for factors in common as you went your way along. Now this next one has the same kind of feel to it. You may not have seen it before, that is. This is called the Euclidean Algorithm. And the Euclidean Algorithm is a different way of doing this, a different approach. What you do is you divide the larger number by the smaller one. You take the previous divisor and you divide that by the remainder, and you repeat until you get a remainder of 0. So you may not know what all those terms mean. There's a lot of vocabulary there, but let's take a stab at doing it, and you'll see how it works. The first one you should be able to decipher what it's talking about doing. What am I going to do? Great, 126, the larger value, and I'm going to divide by 72. Okay, so how many times will 72 go into 126? Once. 1 times 72 is 72, and what do I get as my remainder? 54. Whoops. 54. All right, then what I do is I take the previous divisor, that's my 72, and I take my remainder. And I do the division again. Larger number underneath, smaller value on the outside. So now I'm doing 54, and I'm looking at it dividing 72. So how many times will 54 go into 72? Once again. 1 times 54 is 54. I promise sometimes it will go in more than once. What's my remainder? 18. And then I'm going to take the remainder and the divisor, and I'm going to do it again. Okay, so what's going to go where? 8 to the outside. How many times will 18 go to 54? It'll actually go in 3 times. What's 3 times 18? It's 54. So what's my remainder? 0. So it says we're going to do this until I get a remainder of 0, which I did. And then it tells you the last divisor, that is the last thing that you divided by, is your greatest common divisor. So it's a repeated division step. You're just stepping through division several times, and the last thing that you divide by is your greatest common divisor. Euclidean algorithm. All right, that was our last of the greatest common divisors. Now we're going to look at least common multiple, and you're going to see some of these kinds of things, these different processes, again from a different perspective. So least common multiple is actually, think about back to about 3rd grade when you learned, which is not where you're learning now necessarily, but when you were in 3rd grade, you probably learned multiplication tables, agreed? And somebody could probably tell me what the multiples of 3 are. Somebody tell me what your multiples of 3 are. Okay, so it's the multiplication tables of 3, right? Those are multiples of 3. We can do it for whatever number we would like. So when we're looking for a least common multiple, first of all, it has to be a multiple. Multiples, with the exception of the first one, are bigger than the number we're talking about. So if I talk about the multiples of 3, I'm talking about the 3 as the smallest one, and I'm looking at 6, 9, 12, numbers that are bigger than 3. Factors does the opposite, right? Factors are things that break a number apart, smaller than it was before. So the reason I want to bring this up is because the word greatest for greatest common factor or divisor, and least for least common multiple often throws students for a loop. Because you think when you're hearing the word greatest that it's something that's large. But you have to remember that that's a modifier. It's modifying the word factor or the word divisor. It's the greatest factor. The factor's smaller than the numbers we're dealing with typically. Okay? And a multiple, what's a least multiple? But least what? Least multiple. So the multiples are always values that are larger than what I'm dealing with. So typically speaking, a least common multiple is larger than a greatest common factor. Typically speaking, a least common multiple is larger than a greatest common factor or divisor. Okay. What you want to focus on is the word of what you're looking for. That is, you're looking for a multiple. You're looking for a factor or a divisor. The least and the greatest will modify, will describe what that word is. Don't go looking for something large just as it says greatest. First, you got to look factors before you can start talking about whether it's a large factor or not. Okay, so let's take a look at finding a least common multiple. There's several different approaches to this. The first one is the number line model. It's equivalent to a colored rods method. It's another one that your book talks about, that's why I bring it up. So I wanted you to know that if you see it from your book or if you see it in another book, that these are the same kind of method. What this does is it shows multiples of all numbers on a number line and intervals of each value, and then it finds the first value where the intervals coincide. So let me show you what this looks like, and we're going to do it from the number line model. And I'm going to draw my number line here at the bottom, because I'm not going to go looking for it today. So we're going to start at 0. I'm cheating because I know how long I want it, but you can go and do this indefinitely, okay? So I went out to 30. And then I'm going to use the colors that I have and make the lines as long as I want them to be. So I'm going to use this line, and I'm going to make it a different color, at least in theory. You know, I'll use red. And so each of the reds that I draw are going to be lengths 6. So I'm going to draw one length of 6 that goes from 0 to 6. And then on the end of that, I'm going to draw another one. So imagine actually putting rods of color down. So this is called also the color rod method. Each of my rods of red color are worth 6. There's 6 units, whatever it is, long. So here's one length of 6. Here's my second length of 6. Here's my third length of 6. And I can keep going in lengths of 6 for as far as I need to. I happen to know I'm going to go to 30, but if I didn't know that and I didn't already correspond, then in fact, let me leave that one off just so you can see what I would do. We'll do the blue one here next. We're going to do lengths of 15 next. Okay, so I'm starting with the same 0. I'm just going to stack them on top of each other. And I'm going to go until I get to 15, which is right here. Okay, and what you'll notice is that where 15 ends is in the middle of one of my red rods. So I'm not there yet. What I want is I want to stop drawing my rods at the point where they line up. One of them, they both end, the end of both rods actually ends in the same spot. And the cool thing is if I put another one of these on here, 15 later, I end up at 30, and that's exactly where I had to stop from before if I'd left it drawn with this one. So they both end up at 30, and this is a very visual way, and tactile learners, you know, the ones who want to touch everything, you can do this with actual rods. Okay, sometimes they're called Cuisenaire rods. You see that, but that's the brand name, that's what I'm using. But you'll see those used, but they're colored rods, and each color is a different length. Okay, so this is one way of doing it. Now, you can do the same sort of thing with intersection of sets. Okay, now we did an intersection of sets method before, and what it is you list out all of the factors. That's what we did it before. And we looked for what factors they had in common. And it was the greatest one they had in common that we were interested in. Do you remember that? Okay. But what did we list? The list was of factors. But what I'm trying to find here is the least common multiple. So what is my list going to be here? Multiples. All right. So I'm going to do multiples of 12 to start with. And so I'll start with 12. What's my next one? 24, and you don't exactly know where you're going to stop, so just, you know, list out 5 or 6 of them and then do the other list and see if you've got enough. I mean, that's really what you're doing. So what's after 24? I hear fewer and fewer responses. Okay, let's stop there. It may be far enough, right? We'll see. Now we're going to do the same thing with 15. So list out some 15s. more just for fun. What's more? 75. What I'm looking for is the least number that matches in both lists. And I have one here, right? It's 60. So my least common multiple is 60. It's the least one, the first one in the list. Whereas before, I was looking for the greatest one in the list because I already listed factors out. Okay? I didn't actually write this one down over here either. So the least common multiple here was what? It was 30. I'll fill that back in. All right. So this kind of has the same feel to it. It just doesn't have a picture, right? I mean, it's the same thing. You're listing them out. You're drawing them out. But you're just doing it from a picture point of view or from a numerical kind of a pattern point of view. All right, let's do one that's a little bit different. Let's do prime factors. Okay, so prime factorization, what it does is it does just like what the prime factorization did before. First thing you do is you actually figure out what the prime factors are for all the numbers you're working with, okay? So we're going to do these three numbers, 90, 50, and 20. And I know you can use factor trees, and I know that's what you're more common or more accustomed to, so I'm going to do the other one that I showed you. We're just sort of building down, okay? And we're going to do it, I'm going to do it with least numbers as far as we can anyway, because it's going to make things sort of line up a little bit friendlier. All right, what's the smallest number that divides 90, prime number? 2. 90 divided by 2? Good. Now, the smallest number that divides 45? 3 actually works as the smallest. 15. Smallest that divides 15?
3.
And I get 5. Good. No, the reason I'm going to choose the smallest is just because I want to see if they're all listed in order, it'll be easier to sort of notice, oh, look, they all have 2 and it's all listed first. If you do it out of order, it's not going to hurt anything. It's not going to be wrong. It's just going to mean that you have to look at it a little bit more carefully to pick things out because they're not going to line up in the same spots. Yes. All right, let's do 50 now. Smallest thing that divides 50. 2. Smallest prime anyway. 2. And then I get 25. And then 5 and 5. Good. Now let's do 20. Smallest that divides 20. Prime number. 2 and I get? Okay. So number 1 said, construct the prime factorization of each number. Well, we've broken it down. We actually haven't constructed the prime factorization yet, so let's do that. So my number 90, if I list it in order, I have 1, 2. And then I have 2 3s. I'll write it as 3 squared. And then I have 1 5. The number 50 is what? The 2 times 5 squared. And the number 20, 2 squared times 5. Okay, so that's actually what we did, number 1. Construct all the prime factorizations for each number. Number 2 is we're going to choose all prime factors in each factorization. So, take a look. We're going to find my least common multiple. And I want to list out all primes that I see listed anywhere in any of those numbers. So what do we list first? There's a 2. What else is there? There's a 3. And there's a 5. So you're going to list all of them out. If it's in there, in any of the numbers, it's part of the least common multiple. Next thing to do, though, is it says you're going to list each prime with the largest exponent. So what is the largest exponent you see on any of those 2's? 2 squared, right? There's a squared. What is the largest exponent you see on any of the 3's? It's a squared. And largest exponent you see on any of the 5's? Squared. No, yeah, squared right in the middle, right? Yeah. It's not always the same. That's just the way it's worked out. And then if you're wanting to find out the least common multiple, typically we would multiply these back out together. So 2 squared is, 3 squared is, and 5 squared is 45. So if you grab your calculator, or really quickly if you can by hand or your head, we need 4 times 900. Thank you. That was pretty quick. Good job, guys. 900. So the least common multiple is 900. And I don't know about you, but that intersection of sets methods from before, I don't want to list out multiples of 20 until I get to 900. Okay, could I? Yeah, I mean, we could do that. It might take quite a while. It's not very efficient. It would work. Not very efficient. So this is a fairly efficient way of doing this. Efficient means quick, okay? All right, let's take another one. This is division by primes. Probably my favorite, okay? Division by primes. And we did a division by primes with the greatest common divisor earlier. And what we did is we put all the numbers that we were trying to compare underneath the division, or in this case, above a division. And that's what we're going to do here too. So I've got 90, I've got a 100, and I've got a 20, and I would do like this. This is exactly what I would do if I were doing greatest common divisor, right? This is yes.
Yes.
Yes, thank you very much. Got some verbal. All right. What we're doing is we're looking for, when we look at this, prime numbers that would divide all three numbers. Or all two numbers, or whatever you have. Here I have three. So what's a prime number that will divide all three of these? 2. And then I'm going to divide each of them. So what's 90 divided by 2? 100 divided by 2? And 20 divided by 2? 10. Now I look at the numbers 45, 10, and 50, or 50 and 10. And I do the same thing. I want to know the next smallest, if you will, prime number that divides all three. 5. And if you don't happen to find the smallest one, it will become evident later and it's fine. But kind of go in order. So we're going to do 5. So 45 divided by 5. 50 divided by 5. And 2. Okay. Now, prime number that divides 9, 10, and 2? There isn't one. But what we are going to do is notice that there is a prime number that will divide a couple of them, right? To make it smaller. What prime number will divide a couple of them? 2. 2 will divide the 10 and the 2. So we're going to draw it one more time. We're going to divide it by the 2. The 9 is just going to be rewritten. I recognize we did not divide it. It looks a little bit odd. It'll be okay. We're just going to leave it alone. But the 10 divides by 2 into 5, and the 2 divides by 2 into 1. Now, all the numbers that are at the bottom here, 9, 5, and 1, they don't have any factors except 1 in common, right? Okay, so then I'm done. At that point, I'm done. Now, notice if I were doing this problem from before, I wouldn't have done that last step at all. Greatest common divisors, I wouldn't have done what I just did with that last 2. Okay? But for least common multiples, I need that one more step. Yes, Haley?
So if only one person have, like, if you choose actually.
Well, look at that 9, right? That 9 is actually not prime, right? So, yeah, I mean, like, so the question of whether or not should I continue with the 3s, it's not necessary. I mean, if you did, it wouldn't hurt anything. You still have the right answer, but it's not going to help you at all either. So it's not a matter of getting prime numbers at the bottom. It's a matter of getting all the numbers at the bottom to not be really divided by the same value. Did everybody follow what her question sort of was leading to? Of whether or not I should keep dividing if something's not prime? And the answer is no, I don't need to. I just need the numbers at the bottom to not be divisible by anything in common. Okay, here's the cool thing about this. Every number that you see along the side and along the bottom, when you multiply them all together, that's your least common multiple. How nice is that? That's pretty friendly, isn't it, Lauren?
I do lots of time.
Oh, no, it's good stuff. Least common multiple. So it's going to be, and again, it doesn't matter what order I really write them in. I've got a 2, I've got a 5, I've got another 2, I've got a 9, and I've got a 5. And just for fun, we'll write the 1. What happens when we multiply these?
900.
You get 900. Yes, you do. So I like this method. I don't have to do any comparing. When I'm done, my answer's just all right there. Yes.
So if you're doing more than just 2 numbers,
Yes.
and there are 2 of them that can be divided by the same factor, you do that?
Yes.
Okay.
For least common multiples.
Okay.
You would not do that for greatest common factors. For greatest common factors, you legitimately have to have it be a factor of everything in order to do this.
Okay.
For least common multiples, you don't.
Okay, what if like 9 and 10 would have had 1 together and 10 and 2?
Just do it 2 at a time.
Okay.
Yes. That's a good question. So her question is, what happens if this had said, maybe this had said 6. Let's pretend that said 6. You just do it 2 at a time. So you decide, oh, I'm going to look at the first one and the last one. They have a 3 in common, so I'm going to divide the 3 out and get the numbers down here. And once you do that, you're going to still see that the first one, or the second one, and the third one have 2 in common, and you can go at it again. Yeah. So you can do it 2 at a time if you'd like, but just do it 2 at a time when they no longer all 3 have something in common. Okay. All right, there is a relationship between greatest common divisor and least common multiple. That is, if I find one, I could go through all the steps to find the other, or I could use a formula that relates them together. That's kind of handy, right? The formula looks something like this. The greatest common divisor of 2 numbers A and B times the least common multiple of those numbers A and B. So this A, B in parentheses is just telling you it's the 2 numbers I'm talking about. Okay? It's just designating the least common multiple of what? Okay? If I multiply the greatest common divisor and the least common multiple, I get the product of the 2 numbers that I started with. Okay, I'm guessing example 4 must have happened last time. Oh, no, it's the very first thing we did today. Okay, so example 9 tells us that we're going to find the least common multiple, but we're going to do it using the greatest common divisor, least common multiple formula, this one up here, and the results from example 4. So example 4 was the Euclidean algorithm that we did, very first thing up here. We found out that the greatest, oops, one went off. There we go. The greatest common divisor of 72 and 126 was 18. Okay? So we know from this that the greatest common divisor is 18. Agreed? So what this formula says is that if I multiply the greatest common divisor and the least common multiple, I should get the factors 72 and 126 multiplied. And I know the greatest common divisor. I already found it. It's 18. So if I want to find the least common multiple, what would I do? Right. So I'm going to multiply the 72 times 126, and then I heard a couple people tell me I'm going to divide by 18. So what is 72 times 126, and then divide by 18? Did you divide by the 18 yet? 504? Okay. And you can do it in 2 steps. I don't do anything. Make sure you divide by the 18. So I don't know about you, but I'd rather use the fact that I already know to be able to find the other piece instead of recreating the wheel for the other piece, right? That's a really handy feature if you're asked to do both. All right, let's take a look at an example with context. Because you guys are going to do context probably yourself later, right? Doesn't look like anybody's going to do full 3. Bummer. 2 bike riders ride in a circular path. The first rider completes 1 round in 12 minutes, and the second completes it in 18 minutes. If they both start at the same place and at the same time, and they go in the same direction, how many minutes will they meet again at the starting spot? Okay, so this is like what would happen if you were running upstairs with a rock, right? They're going around the circle, okay? Going around the lake, you're going around, in this case, the circular path. All right, so the first rider completes 1 round in 12 minutes. The second one completes it in 18. So after 12 minutes and 18 minutes respectively, they're not going to be at the same place, right? If I look at 12 minutes, one will have finished the first round, the other one won't have. If I look at 18 minutes, the second one will have finished the first round, the first one will have gone far further. So the question is, how long will it be before they meet at the same time, the same place again? Okay, at the starting spot. What is this asking you for? This is the least common multiple, right? I want to find the least common multiple of what? 12 and 18. How do I do that? Well, you got lots of ways. How do you want to do it? You like the listing method, okay? So we're going to do the listing method for Brennan, and we'll just see how long it takes. So we did 12s before though, didn't we? Did we go out to 84 or thereabouts? Yeah. Okay, so 12, 24, 36, 48, 60, 72, and 84. I think that's plenty for this one. How about 18? We'll do one more just for fun. What's after 36? 44? 54. That sounds better. Okay. We've gone far enough on this one. This one's actually occurred pretty quickly. They actually had a least common multiple of what? 36. So 36 what? Minutes. So after 36 minutes, they're both back at the starting spot. But they cover different amounts of distance, agreed? Okay, last question in this section. We'll do group work for this section next time, so you're not due next time on this section. Example 11, that doesn't mean you shouldn't start. Yeah, heard that. All right, example 11, can two non-zero numbers have a greatest common multiple? Explain your answer. Can you have a greatest common multiple? When we talk about least common multiple, we talk about greatest common factor. Can you have a greatest common multiple? Yeah, it would keep increasing every time, right? So let's think about the last problem we did, because we already listed some things out, which was nice. We found the first one they had in common, right? But provided that these two gentlemen or ladies or whatever could keep going around at the same pace, you know, forever, would they not keep eventually crossing paths back to the starting spot? Yeah. We do it over and over and over and over again, right? It would happen at 36 minutes, and then when would it happen? It would happen at 72, and then it would happen 36 minutes after that, and 36 minutes after that, and 36 minutes after that. It would keep happening, right? Every other 18 factor, 18 minutes, and every third for the 12. Every 3 laps for the 12-minute person, and every 2 laps for the 18-minute person they cross paths at the starting spot. Okay? So, what's your answer? No. And I'm not going to write any details. I want you to write the details down that make sense to you. Reference the last problem if you'd like, or whatever. The answer is no. It will keep happening over and over and over again. Because once you have a multiple, you can double it or triple it or whatever you'd like, and it will be in the same listing of numbers if you want to think about the list over and